You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Artificial intelligence, machine learning, and deep learning are three terms often used interchangeably in casual conversation, but they represent distinct levels of scope and focus. Artificial intelligence, or AI, is the broadest concept, encompassing any effort to create systems that exhibit human-like intelligence. This could mean rule-based reasoning, problem-solving algorithms, or adaptive learning techniques. Machine learning, or ML, is a narrower category within AI, emphasizing systems that learn patterns from data rather than relying solely on fixed rules. Deep learning, or DL, goes even further, representing a subset of ML that uses multi-layered neural networks to capture complex and abstract patterns. Understanding the relationship between these three levels, AI as the umbrella, ML as a major branch, and DL as a specialized branch of ML, provides clarity and prevents confusion. This distinction matters because it shapes how we evaluate tools, methods, and claims in both academic and practical contexts. Artificial intelligence, as the broadest concept, sets the stage for all methods that aim to replicate, simulate, or approximate human intelligence. AI is not tied to a single approach but embraces a range of techniques, from logic-based systems to probabilistic models. A chess-playing program, a self-driving car, and a speech recognition system are all examples of AI, even though they rely on different methods. The unifying factor is the attempt to perform tasks that we associate with intelligent behavior. By viewing AI as this overarching field, learners can appreciate its diversity and adaptability. It is similar to thinking of medicine as a field. Within it are multiple specialties, each with its own techniques, yet all share the common goal of promoting health. Likewise, AI's unifying goal is creating systems capable of intelligent action. Machine learning narrows this scope by focusing on one powerful idea. Systems can improve performance by learning from data. Instead of being explicitly programmed with every rule, ML systems are trained on examples. A spam filter, for instance, learns to distinguish between legitimate emails and junk by analyzing thousands of labeled messages. The system identifies patterns and generalizes them to new cases, adapting to evolving spam tactics. This reliance on data-driven learning makes ML flexible and effective across many domains. By emphasizing learning rather than manual instruction, machine learning represents a major evolution within AI. It shifted the field away from rule writing by experts and toward models that could adapt and evolve in ways closer to human experience. Deep learning represents the next step, building on the foundations of machine learning. It employs artificial neural networks with many layers, often called deep architectures, to capture patterns that simpler models might miss. Each layer processes data at increasing levels of abstraction. For example, in image recognition, early layers might detect edges and shapes, while later layers identify complex structures like faces or objects. This hierarchical processing allows deep learning models to excel in domains like vision, speech, and language. Unlike traditional ML, which often requires feature engineering by humans, deep learning models learn these features automatically from data. This automation makes them extremely powerful, but also heavily dependent on large datasets and significant computing power. Deep learning has driven many of the most visible AI breakthroughs in the past decade. It is important to remember that not all AI involves learning. Early approaches relied heavily on rule-based systems and symbolic reasoning, where knowledge was explicitly encoded into logic rules and decision trees. These systems were useful in specific contexts, such as expert systems for medical diagnosis, but they lacked flexibility. They could not adapt to new information outside their programmed rules. Although overshadowed today by machine learning, rule-based AI remains relevant in contexts where rules are clear and predictable, such as scheduling or formal verification tasks. By contrasting these early approaches with data-driven learning, we see how the field evolved to tackle complexity. Symbolic reasoning represents AI's roots, while machine learning and deep learning represent its more adaptive branches. The spectrum of machine learning algorithms illustrates the diversity within this subfield. At one end are simple models like decision trees, which split data into branches based on conditions. At the other end are more complex techniques, such as support vector machines, which find optimal boundaries between classes of data. In between lie clustering algorithms, ensemble methods, and Bayesian models, each suited to particular types of problems. This variety shows that machine learning is not a single technique, but a toolbox of approaches. Choosing the right algorithm depends on factors such as the nature of the data, the scale of the problem, and the need for interpretability. For learners, recognizing this spectrum is key to understanding why different methods coexist and remain useful despite the popularity of deep learning. At the heart of deep learning lies the concept of artificial neurons, simplified mathematical functions inspired by biological brain cells. Each artificial neuron takes input, applies a transformation, and produces output that can feed into other neurons. While much simpler than real neurons, these artificial counterparts capture the idea of distributed processing and collective decision-making. Networks of these units can model complex, non-linear relationships, making them especially powerful for tasks like recognizing speech or images. Understanding this foundation helps demystify deep learning. Rather than being magical, it is an extension of simple mathematical building blocks arranged in large, layered networks. The sophistication arises not from individual neurons, but from the scale and depth of their connections. One of the defining advantages of deep learning is its ability to create hierarchical representations. Each layer in a deep network extracts increasingly abstract features from raw input. For example, in speech recognition, early layers may capture basic sound frequencies, middle layers detect phonemes, and deeper layers recognize words or sentences. This layering allows deep networks to learn directly from raw data, bypassing the need for humans to manually design features. The result is greater adaptability and performance in tasks where complexity overwhelms traditional methods. This hierarchy mirrors how humans perceive and interpret the world, building understanding step by step. For learners, appreciating hierarchical representation explains why deep models often outperform shallower ones in challenging domains. A key differentiator between machine learning and deep learning is their reliance on training data. While all ML methods depend on data, deep learning thrives on massive datasets. A decision tree might work well with thousands of examples, but a deep neural network often requires millions. The reason is that deep networks have vast numbers of parameters to tune, and without sufficient data, they risk overfitting memorizing noise rather than learning meaningful patterns. This dependency makes deep learning powerful in data-rich environments, but less practical in data-scarce ones. Understanding this reliance helps explain why industries with abundant digital data, like social media and e-commerce, have been fertile ground for deep learning breakthroughs. The computational demands of deep learning are another critical factor. Training large neural networks requires enormous processing power, often provided by graphics processing units or GPUs. These specialized processors excel at handling the parallel computations necessary for deep learning. In recent years, additional hardware like tensor processing units, or TPUs, has been developed specifically for AI workloads. The need for such resources explains why deep learning only surged in popularity once hardware and cloud infrastructure caught up. Without powerful computers to crunch the numbers, the models would remain theoretical. This interplay between algorithms and hardware is a recurring theme in AI history, illustrating how progress depends on both ideas and the means to implement them. The performance gains of deep learning have been striking. In fields such as computer vision, natural language processing, and speech recognition, deep models have consistently outperformed traditional machine learning techniques. For example, convolutional neural networks surpassed earlier approaches in image classification competitions, and transformer models revolutionized language tasks like translation and summarization. These gains are not marginal, they often represent leaps in accuracy that open entirely new applications. The ability of deep learning to capture complexity and scale with data has made it the dominant force in modern AI. However, this dominance should not overshadow the continued relevance of other approaches, which may be more practical in settings with limited data or computational resources. Interpretability, however, reveals one of the trade-offs between machine learning and deep learning. Traditional models like decision trees or linear regression are relatively transparent, allowing humans to understand how predictions are made. Deep learning models, in contrast, often operate as black boxes, with decisions emerging from the interaction of millions of parameters. This opacity raises challenges in contexts where accountability is crucial, such as healthcare or finance. While techniques for explainable AI are being developed, interpretability remains a relative strength of simpler ML methods. This difference highlights the importance of choosing the right tool not only for accuracy but also for trust and transparency, depending on the domain. Scalability is another area where distinctions matter. Traditional machine learning methods often reach a plateau in performance as data volumes increase, while deep learning models continue to improve with more data and compute. This scalability makes deep learning especially suited for large-scale applications like image recognition across billions of photos, or language models trained on entire libraries of text. Yet scalability comes with costs in energy, hardware, and environmental impact. Recognizing these trade-offs helps learners appreciate why deep learning dominates headlines, but also why researchers continue to explore more efficient alternatives. The scalability advantage explains both the excitement and the concerns surrounding the deep learning revolution. Even as deep learning dominates, some areas of AI remain rooted in methods that do not involve learning from data. Search algorithms, optimization routines, and symbolic reasoning systems continue to play vital roles. For instance, pathfinding algorithms are essential in navigation systems, while logic-based approaches are critical in verification tasks. These methods demonstrate that AI is not exclusively about machine or deep learning. Instead, the field encompasses a wide array of approaches, each suited to particular challenges. By recognizing the continuing relevance of AI without learning, learners avoid equating AI solely with the latest trends and maintain a broader perspective on the field. Modern AI solutions often integrate multiple approaches, combining symbolic reasoning with machine learning or merging rule-based logic with data-driven methods. Hybrid models leverage the strengths of different techniques, addressing the weaknesses of any single approach. For example, combining symbolic reasoning with deep learning can improve transparency while retaining flexibility. These integrations reflect the complexity of real-world problems, which rarely conform to the neat boundaries of one method. For learners, this blending underscores that AI is best understood not as a competition between paradigms, but as an evolving toolkit. The most effective solutions often arise from synergy rather than exclusivity. Finally, it is worth reflecting on why these distinctions matter. Understanding the boundaries between AI, machine learning, and deep learning helps clarify vendor claims, evaluate technologies, and set realistic expectations. It allows learners and professionals to distinguish between a broad vision, a methodological approach, and a specialized subset that currently drives much of the excitement. Without this clarity, discussions risk being vague or misleading, hindering both decision-making and learning. By mapping these boundaries, this episode equips you with a framework to interpret the field more accurately, ensuring that future lessons build on a solid foundation of understanding. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. A useful way to frame the relationship among these concepts is to think of AI as the what, machine learning as the how, and deep learning as a particularly powerful how. AI defines the overarching goal, building systems that can act intelligently. Machine learning specifies a method for reaching that goal, namely by allowing systems to learn patterns from data. Deep learning then represents a specialized implementation of machine learning, one that uses many layered neural networks to achieve extraordinary results. This layered framing helps cut through confusion and provides a mental model for remembering how the terms connect. It is like thinking of transportation. AI is the idea of moving people and goods. Machine learning is the invention of vehicles, and deep learning is the development of high-speed trains or airplanes that push the boundaries of performance. Much of today's excitement about AI comes from deep learning breakthroughs which dominate headlines and public discussion. The surge of generative models capable of creating text, images, and audio has captured attention because they feel almost magical compared to earlier tools. While machine learning has long powered recommendation systems and predictive analytics, it is deep learning's dramatic successes in vision and language that fuel the current hype. This focus is not unwarranted. Deep learning has delivered remarkable advances, but it can sometimes overshadow the broader field. Recognizing deep learning's centrality in today's discourse helps learners understand why the term AI is so often conflated with DL, even though AI encompasses far more than just neural networks. Machine learning remains indispensable across industries, even apart from deep learning. Fraud detection in finance relies on ML models that analyze transaction patterns and flag anomalies. Recommendation engines on streaming platforms and online shops are powered by algorithms that learn user preferences. Predictive analytics in healthcare use machine learning to identify risk factors and suggest preventative actions. These applications illustrate that traditional machine learning methods continue to deliver immense value, often with less complexity and lower computational requirements than deep learning. For businesses, ML's balance of accuracy, interpretability, and efficiency makes it a practical choice. For learners, these use cases demonstrate that ML's relevance extends well beyond academic theory. Deep learning, however, has been the driver of progress in tasks that require interpreting complex sensory data. In computer vision, deep models have surpassed human-level performance in some benchmark tasks, enabling facial recognition, autonomous vehicles, and advanced medical imaging. In speech recognition, deep architectures allow real-time transcription and translation, transforming accessibility and communication. In natural language processing, transformers built on deep learning have enabled conversational agents that can generate fluent, context-aware responses. These breakthroughs illustrate how deep learning pushes the frontiers of what machines can do. They also highlight why deep learning is resource-intensive. The complexity of these tasks requires massive data and computation. Learners should see deep learning not as a replacement for ML, but as its extension into domains of greater complexity. Machine learning has its limits, and recognizing them is critical. Algorithms are only as good as the data they are trained on. If the dataset is incomplete, biased, or too small, models can produce unreliable results. Overfitting is another challenge. Models may perform well on training data, but fail to generalize to new cases. Furthermore, many ML methods require careful tuning and expert oversight to achieve optimal performance. These limitations remind us that machine learning is not a magic bullet. It is a powerful method, but one with constraints that must be understood and managed. For learners, this awareness fosters healthy skepticism and encourages careful evaluation of claims made about ML systems. Deep learning also has limitations despite its striking successes. One issue is opacity. These models often function as black boxes, making it difficult to explain why they make particular decisions. This lack of interpretability can be problematic in sensitive domains such as healthcare or law. Deep learning is also resource-intensive, requiring enormous amounts of data and energy, which raises questions about sustainability and accessibility. Additionally, deep learning models can be vulnerable to adversarial attacks, where small, imperceptible changes to input data cause incorrect outputs. These shortcomings remind us that every powerful tool comes with trade-offs. Appreciating the limits of deep learning tempers enthusiasm with caution, ensuring learners develop balanced expectations. Hybrid models are an emerging trend, aiming to combine the strengths of different approaches. By integrating symbolic reasoning with deep learning, researchers hope to build systems that are both powerful and interpretable. For example, a hybrid medical diagnostic system might use deep learning to process images while relying on symbolic rules to ensure that explanations are transparent to doctors. These approaches reflect a recognition that no single method solves all challenges. Instead, blending paradigms can yield systems that are more robust, trustworthy, and adaptable. For learners, hybrid models illustrate the evolving nature of AI research, where boundaries between categories blur in pursuit of better solutions. Reinforcement learning intersects with both machine learning and deep learning, adding another dimension to the landscape. Unlike supervised learning, which relies on labeled data, reinforcement learning focuses on agents that learn through trial and error in an environment. Deep reinforcement learning combines neural networks with this feedback-driven approach, enabling breakthroughs in robotics and game-playing AI. For instance, AlphaGo's success in Go came from combining deep neural networks with reinforcement strategies. This intersection highlights how different branches of AI complement each other. Reinforcement learning illustrates that the boundaries among AI, ML, and DL are not rigid walls but overlapping zones of collaboration. It is helpful to compare machine-based learning with human learning to appreciate their distinctions. Humans learn through experience, context, intuition, and social interaction, often generalizing from sparse data. A child can recognize a dog after seeing only a few examples, whereas a machine may require thousands. Machines, however, excel in precision and consistency, processing massive datasets without fatigue. Understanding these differences helps clarify both the promise and the limitations of AI. It also frames ongoing research questions. How can machines learn more efficiently, and how can humans and machines complement each other's strengths? For learners, this comparison grounds the subject in relatable terms while underscoring the uniqueness of human cognition. The distinctions among AI, ML, and DL are reflected in research communities as well. Academic and industry groups often align around particular approaches, influencing funding, conferences, and publications. Some communities emphasize theoretical advances in algorithms, while others focus on applied deep learning breakthroughs. These distinctions also reflect institutional priorities. A startup may pursue deep learning to build cutting-edge products, while a government research lab may focus on interpretable ML for regulated industries. Recognizing these differences provides insight into why certain methods dominate at different times and contexts. For learners, it highlights that the field is shaped not only by technology but also by organizational culture and goals. Definitions of AI, ML, and DL have also evolved over time. Decades ago, AI was primarily associated with symbolic reasoning, and machine learning was considered a niche method. Today, the dominance of deep learning has shifted perceptions, with many people equating AI itself with neural networks. These evolving definitions can cause confusion, but they also reflect the dynamic nature of the field. As technologies advance, the boundaries shift, and the terms adapt. For learners, this historical perspective reinforces the importance of staying flexible in how we use language. Clarity requires not only understanding current distinctions, but also recognizing that definitions will continue to change as the field progresses. Communicating these differences to non-experts is an important skill. Business leaders, policymakers, and the public often encounter the terms AI, ML, and DL without clarity on what they mean. Misunderstandings can lead to misplaced expectations, poor decisions, or inflated hype. Being able to explain these distinctions in simple, accurate terms ensures that conversations about AI are productive and grounded. For example, clarifying that deep learning requires massive datasets while simpler ML methods may suffice in many contexts helps decision-makers evaluate costs and benefits. For learners, developing this explanatory skill is valuable not only for exams or interviews, but also for professional credibility. These distinctions also have regulatory and policy implications. Laws and ethical guidelines often hinge on how terms are defined. For instance, regulations around transparency may apply differently to interpretable ML models versus opaque deep learning systems. Policymakers need clarity on what they are regulating, and practitioners need to understand how definitions influence compliance. This interplay underscores that terminology is not just academic. It has real-world consequences for law, governance, and ethics. Learners should recognize that understanding these distinctions equips them to engage more effectively with the broader societal debates around AI. Looking ahead, the future directions of AI, ML, and DL may converge or diverge in interesting ways. Deep learning will likely continue to dominate high-profile applications, but new paradigms may emerge to address its limitations. Advances in hybrid models, neurosymbolic approaches, or efficient learning techniques may shift the balance again. At the same time, traditional ML will remain valuable where data is limited or interpretability is critical. AI as the umbrella field will continue to expand, incorporating not only these subfields but also emerging areas like quantum computing and bio-inspired algorithms. For learners, this outlook emphasizes adaptability and the importance of keeping an open mind as definitions evolve. Ultimately, this episode provides a framework for learners to navigate the field with clarity. By distinguishing AI, ML, and DL, you can interpret claims more accurately, evaluate technologies more critically, and approach future episodes with a stronger foundation. These distinctions will serve as guideposts throughout the course, reminding you that AI is not monolithic, but a layered field with multiple approaches and trade-offs. With this framework in place, you are better prepared to engage with both the excitement and the complexity of artificial intelligence, understanding not only what it is, but also how its methods differ and complement each other. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.